We're continuing with section 14.7, optimization in three variables. This is an optional part. The emphasis of the course is to optimize functions of two variables, but we want you to have a little bit of flavor of three variables or more. How do we find local extrema of a function f of x and y and z of three variables? First, you find the critical points. They are the solutions of the equation a gradient of f at a and b and c equal to 0 vector, or equivalently, when f of x and f sub x of a and b and c equal to 0, f sub y of a and b and c equal to 0, and f of f sub c of a and b and c equal to 0. So the solution to those three equations. The next is classifying them. To classify them, this is a little bit different from the functions of two variables because you will have three discriminants. The first discriminant is just f sub x of a, b, and c. Then d2 is going to be the f sub xx of a and b and c, f sub xy of a and b and c, and f sub yx of a and b, c, and f sub yy of a and b and c. Again, we still always use the different order of mixed derivatives, because if the second derivatives are not continuous, then this method still work. But all the work we put in Calculus 3 in this course is when the second derivatives are continuous, then we find the critical, then we find the local extremas. So D3 is going to be basically all the derivatives that starting with x, and then so xx, xy, xz, and so on and so forth. And so if you pay close attention, you realize that D1 is right about here. You can see D1, which appears here, also appears there, and then D2 is basically this part of the matrix, and D3 is the entire thing. So they are all related basically. Now let's see, how do we use D1, D2, and D3? If P of A and B and C is a critical point of F and all second partials are continuous near P, then D sub 1 is bigger than 0. If D sub 1 is bigger than 0, D sub 2 is bigger than 0, and D sub 3 is bigger than 0, then P is a local minimum. If D1 is less than 0, and D2 is bigger than 0, and as you go, you notice that you actually had D1 and D2 and D1 and D2 in the same way with the functions of two variables. So 2 is D1 less than 0, D2 bigger than 0, D3 less than 0, then P is a local maximum. If D3 is not 0, but neither 1 and 2 are, happens, then P is not a local extrema. If D3 is equal to 0, then the test is inconclusive. So to classify critical points of a function of n variables, and you form the discriminants D1, D all the way to Dn. And then, so Dn is the one with all the derivatives in it, like D3 was. And then you basically take the upper left corner and you make it smaller and smaller to go back to D1. It's just a matrix, and then you make it smaller and smaller, or when you form the end, and you pick matrix of dimension 1 to be D1 dimension 2, D2, and so on and so forth, but they are matrices on the upper left corner. And so, and then from there, if all discriminants are positive, you have a local minimum alternating sign pattern starting with D1 less than 0 gives you a local maximum. So that works for all of them. Let's do an example. Find and classify the critical points of the function f of x and y and z equal to x cubed plus x squared plus y squared plus z squared plus 5z. So the critical points are the solutions of the gradient of f of x and y and z equal to 0 vector. Therefore, take the partial. This one is the partial with respect to x, 3x squared plus 2x. This one is partial with respect to y. And then partial with respect to z, and set them all equal to 0, and then solve. This immediately gives you y equal to 0. And then the other one gives you two values. The first one gives you two values, x equal to 0 and x equal to negative 2/3. And then over here again, z gives you one value. So if you look at this, y is the same for both critical points, but x and z is the same for both of them, but x is different. Now, use these 2 points and find the discriminants. So D1 is going to be form D3, right? D3 is the first one to form, which is going to be fxx, fxy, fxc, then fyx, yy, yz, and so on and so forth. And so D1 is just the one-dimensional matrix on the upper left corner. D2 is this matrix with two-dimensional matrix on the upper left corner, and D3 is the determinant of the entire three dimension, the matrix of dimension 3, and so when you find all the determinants of these are very easy because they're basically diagonal matrices, and finding determinant is easy. And so when you find a determinant, then you have to use the test. So we found D1, D2, and D3. Let's use the test. Then, by the way, the matrix of second order partials is called Hessian, and then the determinants are called the discriminants. And so when I talked about upper left corner, that was the upper left corner of the Hessian matrix, basically. Example, and so we're continuing with the example, and now that we have D1, D2, D3, just plug in the critical points in them, plugging in P and Q in these, and you get the values. Look at the first line. It's D1 positive, D2 positive, D3 positive. Pattern is plus, 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 local minimum. The other pattern is negative, negative, negative. That's neither of them. I can't, not a local extremum.